All right, welcome to Blue Pen Land here. This one is going to be on the test. Let me give you a clue though. Instead of having something that does this, right, the nonlinear one is going to be like a light bulb. It's going to do that, right? State how the resistance of T varies with the current going through T1. Well, if you don't know, right, what it is, then you can actually just read it off like at 1 volt, right? You can read off what the current is and just go, remember R is V over I, right? Now let me just give you a clue though, right? That means that if we look at this graph here, right, and we solve this for I is just V over R, which means the slope of this, the formula for this line is I equals 1 over R, that's the slope, times V, right, plus 0, okay? So that is for a resistor. If it obeys Ohm's law, right, that's for a resistor, and that's that thing, right? In general, though, this little thing here is 1 over the slope is, the slope of the line is 1 over R. So where the slope is small, the resistance is big, and when the slope is big, the resistance is small, okay? So what's happening to this thing is as the voltage increases and as the current increases, right, as we go this way, this thing is getting steeper and steeper. In fact, it starts off with less resistance, right, or more resistance than the resistor, right, and then it has less resistance at the end. Okay, the resistor stays constant, right? Now, how do I know this is less or more resistance than the resistor? Because for a particular voltage, say 3 volts, right, for a particular voltage, the current through T is less than the current through R. Well, if the current's less, the resistance is more because it's a reciprocal relationship, okay? So what's happening to it? Talk about the slope. Slope increases, so the resistance is going to decrease because the slope of this thing is 1 over R, okay? So that is that. But really all we have to do is state. We don't really have to explain it, right? Deduce without numerical calculation whether RT has a greater resistance at current is 0.4. So let's find that. Okay, at 0.4. Well, let's look at this, right? We're going to go R is V over I. I is the same for both of them, but R has a higher voltage, right? So therefore, R has a higher resistance, right? Yeah. And then T is the same current, but it's a lower voltage, right? So T has a lower resistance. R is higher, T is lower. So let me just do that again. So at 0.4 amps, the current is the same for both of these, right? This is the same for both. So whichever one has the higher voltage is going to have the higher resistance, right? These guys are directly proportional. R reaches that current at a higher voltage, so therefore R has a higher resistance. T reaches that current at a lower voltage, right? Here's the voltage. Right? So the T reaches at a lower voltage, so therefore it has a lower resistance. It's pretty simple like that. All right, let's look at the next one here. The components R and T are placed in a cell. Both meters are ideal. Ideal means that this has 0 resistance. R is 0 for this guy. And this guy has an infinite resistance. That is, no current flows through that thing, right? Okay, now keep in mind that this ammeter is going to read the current flowing through both of those. Okay? All right, so let's take a look at this thing. The slider Z of the potentiometer is moved from Y to X. Well, let me give you a clue, whatever this voltage is here, right? Okay, if we slide that thing all the way to this end here, then the voltage here, depending on the resistance of this thing, right, this voltage is going to be the highest. That is, it's more directly connected to this thing. If we slide it halfway, we could get half the voltage, right? If we slide it down here, we get less and less voltage, right? So as we slide it from Y to X, the voltage gets smaller and smaller, and therefore the current gets less and less. Okay. We all have to do is just state, right? Okay. Estimate with an explanation the voltmeter reading when the ammeter reads 0.2 amps. Okay. Well, how are we going to do that, right? We want something that adds up to 0.2 amps, right? So what is this voltmeter going to read when that's 0.2 amps. So we got to go back to the graph. We're looking for 0.2 amps, right? Okay. We want a current to be 0.2 amps, right? Now that ammeter is going to read both of these currents added up. So let's look at, say, 2 volts. Well, 2 volts gives us how much current? That's about 1.4. That's 1.4 amps, or 0.14, sorry. 0.14 amps, and this guy gives us about 0.6 amps. Right? So 2 volts is very, very close, right? In fact, that works. All right, look at that. So that's what you're doing there, is you're just looking for a voltage where it works, okay? Yeah, where when you add them up, right? Let me give you an example of one that doesn't work. Let's try 3 volts, right? Okay, so 3 is going to be about 1.4 plus 2.1. So that would add up to 3.5 amps, or 0.35. Geez, I'm just messing up here. These are point and point, right? So that'd be 0.35 amps, but we're looking for 0.2 amps, okay? So again, you just have to find a spot on here that adds up. Yeah? All right. Sorry about that.